Well, welcome back, everyone. So, left off looking at the minimum degree ordering algorithm. And so I'd like to finish this today and talk about the other ordering methods as well. So we'll see how that goes. Anyway, so we've got this thing called the quotient graph. And this is the exact degree. It's very expensive to compute. This is a cheap bound. And let me illustrate this and show you when it's exact. Okay. Certainly, if I is adjacent only to other nodes, then it's exact. There's no elements at all. If I is adjacent to one element, then it's also exact. And the reason there is because it would only be approximate or an upper bound if, for example, there's an overlap here between these two sets. So here's a set of size 3, a set of size 4. Their set union is 6, not 7. Okay? But when we form this element E1, we would have removed this and pruned this edge because it's not needed. So that overlap wouldn't occur. So that's very important. So when the size of the element list is equal to 0 or 1, this approximate degree bound here, this cheap one, I didn't give a superscript to it, but this bound here, the size of A plus the sum of the sizes of the elements is exact. Okay. But what if there's another element? Okay, if there's another element here, E2 for instance, then it's certainly possible for there to be an intersection, a non-empty intersection between those two sets, E1 and E2. So when the size of the elements list is greater than or equal to 2, then it's an upper bound. But it's a very inexpensive, very simple bound to compute because we're going to go through anyway and prune this list. So we're going to take time, order the size of A sub I, to go through this whole list and remove these edges that I said would make it, exact in this case for elements if they're next to a 0 or 1 element. And so we're going to take that amount of time, and we're going to go through the element list as well here. This should be an E, a calligraphic E. We're going to go through this list here to sum this up, and so that takes this amount of time. So that's the time it takes to compute this bound. And this list here is fixed in size. It's not changing. The elements are either there or they're destroyed. So when these cliques are created, they're created, they exist, and then they're absorbed into a subsequent element. So this L is not changing. So the size of that's not changing. So this could be 100 nodes here. I'm not going to draw 100 nodes. And we don't have to go through all these nodes to count them. Because we just have to keep track of the size of each set, and we just sum up the set sizes. Okay, so that's very cheap, very simple, nothing, that's it, nothing else. This is not the approximation I use, though, because this has been tried, and it doesn't give very good quality orderings. So if you compare this exact degree here versus this cheap bound, this gives much better orderings than this one. And that's what really matters, because the numerical factorization is going to take far more work even than all of this. So it doesn't make much sense to try to use this cheap bound. Okay. Well, I came at this problem sort of by the back door. It was kind of interesting. I was trying to come up with a right-looking method that does the multifrontal method on the fly. This is actually what's inside backslash in MATLAB, although, and I still use this approximate degree in there. The idea here is that if you've got a row I and you've got two cliques, so this is a matrix view of two different cliques, and of course you can't really view it this way. This is kind of abstract because these sets don't have to look like this exactly. But they're going to have an so here's row I, and they're going to have an intersection, and they're going to have some kind of overlap. And what I thought I would try to do is I wanted to keep track of the degree of these rows and columns because I was going to do what's called a Markowitz search, which I haven't discussed much. But the idea is I wanted to do the fill-reducing ordering on the fly. Okay, now I don't do so much of the ordering on the fly. I do a lot of pre-analysis. But I came at it, first of all, from the unsymmetric case, where these cliques are actually rectangular. They're not square. This is a clique in a graph, an undirected graph. So the adjacency matrix is symmetric. This is unsymmetric. But nevertheless, you can still look at this. And the idea here is that, well, I'd like to compute the degree of this row, but I don't want to go through and take the set unions of all these different parts. This set here of column indices, union with that set, union with any non-zeros sitting out here. Okay? And any non-zeros in here, of course, would be consumed, so they're not there. But this non-empty overlap cannot be consumed because this data here can fit in neither front, so they have to lay on top of each other. So I wanted to account for this, and to do this, I thought, well, let me take the size of this current set. So this is K, the pivotal element that just got created, and the question is, can I compute that distance, that size there? If this is an element E, this difference here, this amount, is LE set minus LK. Or actually, to use a better notation, it would look like this. Because that really represents the non-zero pattern of an upper triangular part. Because this is an active submatrix. And so we had the step K here, which had a pivot row that looked like that. And a step E here, which had a pivot row that looked like that. So this is the non-zero pattern of a pivot row, and L would be the non-zero pattern of a pivot column. But anyway, if it's symmetric, they're the same. So I wanted to find out the size of the set difference. And the observation was, and I wasn't looking at minimum degree. I was looking at this unsymmetric ordering. But my observation was that, well, I have to go through each of these columns anyway. And I have to go through each of these rows. And I have to go through their element lists. I have to know, okay, look at these columns and clean up the data structure, remove the extra, do the element absorption, and do this amount of work right here. Okay. So now think of this. I'm going through each of these columns, and I'm going through their element lists. And the question is, what is the size of this set difference? Well, suppose the size of the set intersection is 5. And the total size of LE is 8. Okay. As I visit all of these columns, I can just simply keep track. How many times do I see any given element? So as I'm walking through these columns here, updating the degree and pruning, getting rid of non-zeros and adding them into the current element, getting rid of these edges, doing this amount of work here for every column, for every row, I'm going to see element E 5 times. Well, if I see it 5 times, that's the size of the set intersection. And the size of the set difference is just the opposite of that. It's the total set size minus the size of the set difference. Set intersection, I'm sorry. So I know that if the total size is 8 and I see it 5 times, I don't have to traverse these entries to know that it's 8. That it's 3. The total is 8. I see it 5 times, the difference is 3. Now, in terms of this picture here, that corresponds to the following. Suppose I create, suppose E2 is the kth element. Okay, so I've got E here, and so here's my current pivot element. Okay. Then, and I'm going to have to put in another let's see. Let me just redraw a picture, actually. Oh, there is no element here. I'm sorry. I'm making the problem a little more complicated now. Okay, so here's the new element k. And I'm going to have to go through its neighbors and update the degree. So I'm going to have to go through these nodes right here and either compute one of these expressions. Okay. This one right here for every node would require, and there could be a blizzard of nodes out here. Okay. The exact degree computation would require that I visit this entire graph multiple times, in fact. Think about that. If I have to go and compute the degree of this node, what do I have to do? I have to take the set union of the current clique plus this one plus that one. I've got to visit this entire graph except for these three nodes here. I have to visit basically everything adjacent to any element to update this node here. That's very expensive. I have to visit all this information. So I don't want to do that. This one right here would instead visit, it would go one step less than that. It would not visit this frontier. Okay, it would just say, well, let me just sum up. I'll go to this element. I say, hey, you're adjacent to me. Let me just take your total size and add this size. Well, then I've counted these twice. And then I'll add the size of this. Well, that means I've counted him twice too, and him 3 times. Because he's in all 3 elements. Okay, so that bound is not so great. Actually, when I visit this node, I won't see him at all. So I guess really the frontier should be over here. I won't even visit all of that. So that's expensive. The observation though is that, well, I'm going to be visiting all of these edges anyway. Okay, and what I'd really like to know is what is the intersection of, let's see, I have LK, and the size of the set difference, LE minus LK, is just simply the size of LE minus the size of the set intersection. Right? It's just basic set ideas. So I know this already. This is fixed. I can just look it up. Okay? And so if I start with this number here, let me annotate the graph with that number. What is the degree of E1? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And E2 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What I really want to know is I want to get the number here. The set intersection is what? Between K and E1, it's 3. So I want to say that this is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This right here is the set difference LE2 set minus LK. I want to compute that. And I want to compute the size of this set difference here, E1 minus 2, which is also 9. Picked a bad number. Let me make this 10 and remove one of these edges. So this is 8 now. So I'm starting off with the degree of 10 on E1 and a degree of 12 on E2. And then the observation is I'm going to be visiting each of these edges anyway. So I take 10. There's a 2-pass algorithm here. I look at node I, and I'm not going to try to compute the degree of node I. I'll go through node I and look at its adjacency list, its element list, which is just 1. I'll go to that element and decrement this count by 1 down to 9. And then I'll go here and I'll look at adjacency lists of its elements and I'll say, oh, you're next to E1. Okay, that means I'm in the intersection. If I see this node as I'm visiting K, from K, and I see E1, oh, then this node is in the intersection of K and E1. It's in the intersection. So I'll go here and I'll decrement this count by 1 to 8. And this one down to 11. Then I come here and it gets decremented once again. Oh, I'm sorry, the intersection was 3. I didn't count it right. So when I come here, I'll decrement this to 7, and I'll look here and decrement this to 10. And then when I look at this node, I'll decrement this to 9. And in here, then nothing happens. So you see I've got the number 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is the size of the set difference. And this is 7. 1, 2, 3, 4, 5, 6, 7, which is the size of the set difference. That's LE1 minus LK. Now to compute the degree of node I can go back in a second pass, go to this node and say, well, I'll take 3, which is script A sub I, plus 7, which is 10. But see, that's the exact degree of node I. Well, excluding K itself. I didn't, I forgot to add that in. I'm sorry. So all these sets these two sets are disjointed because I made them so, because I pruned A to remove out anything that appears in any element. So this set here is disjoint from all these others. This set is disjoint from all of those. The pivot element is special. That's added separately. So this plus the size of the pivot element, which I know, plus the size of all the set differences of everybody except for the current pivot element. So the degree of node I is 3, 1, 2, 3, plus the degree of K minus 1, because minus itself. So it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So it's 3 plus 6 for the first two terms, plus 7 plus 9. And that's the degree, that's the bound on the degree of node I. It's an upper bound because what I've just done is it an upper bound? Oh, no, I made a mistake. Node I is not next to E2. I'm sorry. I have to do this differently. I'll call this node J. I'll do him as well. So the degree of node I is 3 plus the degree of K, which is 1, 2, 3, 4, 5, 6, plus 7, which is the set difference, 1, 2, 3, 4, 5, 6, 7. And I've computed the degree of I precisely. I've computed this exact degree precisely because just like this bound did, except now when the size of the element is 2, I get the exact degree. This formula here, when the degree list when the element list is of size 2, this formula gets computed. This formula is the exact same thing as this. Because when E sub I is of size 2, there's 3 terms. A sub I, which is disjoint from everything. LK, which is disjoint from, it's not disjoint from LE, but then there's one set difference. And if I just have a single set difference, it's exact, right? I mean, it's this formula right here. This is precise. I get the size of the set intersection taken away. So when E is equal to of size 2, this formula is exact, but this is an upper bound. It's not exact. It's only when the degree list is of size 3 or more, you have to be inside 3 cliques for this to be an upper bound. And that's the case for node J. Okay, node J is adjacent to almost every, well, not these 3. It might have its own nodes that it's next to. So node J, let me erase this now. Node J is adjacent to every node on this chalkboard. It's adjacent to these 2, plus it's adjacent to 1, 2, 3, 4, 5, 6, which is the size of LK minus J itself, because you don't have the self edges. Plus, it's adjacent to, well, it is adjacent to these 7. Plus, it's adjacent to actually only 7 more, not 9 more. because I don't want to count these twice. So the exact degree would be 2 plus 6 plus 14. That's 8 plus 14 is what? 22. The exact degree is 22, but I'll compute that instead, 24. So I get an upper bound because of this overlap right here between these two elements, two non-pivotal elements right here. So it's a two-pass algorithm. You can't just go and compute this raw. You can't just go to node I and say, let's compute this set difference and go. No. You have to visit all the nodes first to compute the set differences, and then visit all the nodes again and sum up the result. So once you see it as a two-pass algorithm, it's very straightforward. And the total time complexity is the same as this one. Because I go to a node and I visit all of its neighbors in the quotient graph. I don't visit its neighbors this is a neighbor of I in the elimination graph, not in the quotient graph. But I just visit the nodes that are adjacent to this node I in the quotient graph, which takes time proportional to its degree in the quotient graph. This is the degree of a node. If you could move the camera over here. This is the next slide, thank you. This is the degree of the node in the quotient graph, which is not interesting except for this data structure. I mean, it's not the thing it's not the metric I want to use to pick a node. But it gives me, this right here is 1, 2, 3, 4, 5. Well, minus this itself. So I don't have to visit all these nodes. I don't have to visit all these nodes to get these set differences. So the surprising thing is then that at the end of the day, this formula can be computed in time proportional to the size of that list right there, plus the number of elements right here. Which, when you stop and just look at it cold, just look at this formula, that doesn't seem to make much sense. I mean, there's a set difference here, and yet I take constant time to compute that set difference, basically. Amortized time is constant, if you will. Because the total time to compute this summation is just E sub I. Just like that. So this and this take exactly the same amount of time. This is a one-pass algorithm. This is two passes. Okay, so this takes twice the time, maybe. But the quality in terms of the ordering is surprising. In fact, when I first worked on this and applied this idea to minimum degree with the help of Patrick Amestoy and Ian Duff, I was in France, and all good things come from France, right? And we got the code to work. We plugged in this approximate degree from my unsymmetric code. We symmetrized it, put in this minimum degree algorithm. It was pre-existing. That would have been a lot of work for me to construct a minimum degree algorithm all from scratch. There's a lot of machinery in there. So we just added this notion of the approximate degree to it. Got the code compiled and got the test and then ran it on our first 10 or 12 matrices. And then looked at the ordering quality, right? You can do the symbolic Cholesky factorization and get out the total number of non-zeros. You've got the permutation, you permute the matrix and find the symbolic do the symbolic factorization. Here's the number of non-zeros in L. And it was the same as the other algorithm. For the next matrix, it was the same. Down to the last digit, it was the same. Oh, no, this couldn't be. See, I was expecting to get a fast and cheap and quick and dirty, I guess is the word I'm looking for. A quick and dirty ordering algorithm that would be really fast, but at the cost of slightly worse ordering quality. It's much faster to compute than this. I tried it on the third matrix. It was the same. The fourth, it was the same. About 10 matrices, it was only different for one. I thought, well, maybe that was just an anomaly. Maybe I just changed the code. And so I put a print statement in my new code. It says, this is the new code. And it printed out, yes, this is the new code. I was running the new code, and it was working. And it was giving me the same ordering for 9 out of 10 matrices. And the one that was off only by a small amount. And when I tested it on more and more and more matrices, what I found, to my surprise, was that I had a quick and good algorithm, not a quick and dirty algorithm. In other words, the ordering quality did not suffer at all. It fluctuated a little bit because there's differences in tie breaking. There's differences there were subtle differences, but they were just sort of statistical noise up and down, sometimes better, sometimes worse. It was uniformly of the same quality overall. And that was a surprise. That was a stunning surprise. So we just reduced the cost of this algorithm dramatically by going to this approximate degree with no reduction in quality at all. And so that's the minimum degree ordering algorithm. This is the first scan. So this is a trick I use with this essentially like a flag vector. They're all -1. Okay. And when I see an element that's not marked, that's not visited, I set it to the size and then decrement it, and then basically walk through all the adjacencies. So this is just doing this algorithm up here, as you see there. So that's the minimum degree algorithm then in the end. Now the code itself is fairly complex, and I'm not going to go through it in gory detail like I do, for many of the other algorithms. I guess it takes 1, 2, 3, 4, 5, 6. It's about 6 pages in the book. So I'm not going to go through all the details of it. It's very complicated for several reasons. It has to keep track of this idea of supernodes on the fly. They're built on the fly. They're found on the fly. And that's another story. How do you find supernodes? How do you detect them dynamically? You can't do a symbolic analysis because the ordering's not fixed yet. And so the way that happens is as you're traversing through this node here, you want to know, for example, are I and J equivalent in their pattern? Well, what I do is I compute a hash function based upon its adjacency list, such that if two nodes have the same adjacency list, their hash function will be the same. And then I put these nodes in a hash bucket, only the nodes, though, that I'm updating. Because the only place it makes sense to check is the neighbors of K, because these are the only ones that have changed. So you compute a hash function for each of these. So it's not the entire graph. So there's hopefully not a lot of false hash collisions. You'd like a hash collision to occur when they actually match. So the hash function is designed, it's a very simple hash function. It's just the sum of the adjacencies. Like if you're next to node 5, okay, 5. And you're next to node 7, okay, it's 5 plus 7. You just sum up the nodes. Sum up your neighbors. And because it could be in any order. You have to be careful. It's got to be independent of the order. If you see 7 and then 5, it should be the same as 5 and then 7. So the hash function is computed. Then a hash collision means that they might be identical. And then you got to go and check them. Oh, are they the same? Right? Because you could have a false collision. And that's about a page of code right there. I mean, it's out of the 6 pages. There's dynamic memory management in this internally. Because yes, the quotient graph doesn't grow in size. But the only way we can guarantee we have space for the new element is if other edges are deleted. So what happens is then you've got this dynamic graph structure where you're always tacking on a new element at the end of the graph structure. And you know you'll have space for it. You know you'll have space because if you tack on a new element, you know that to create the new element, you must have deleted some edges in the graph. But that space is not crunched and freed up yet. You just have this adjacency list of this other node that's got some holes in it. It's got leftover space in it. So you have this adjacency list that's in space this big, but it's only taking up a piece of that. So you're just tacking on, you have this memory space that's got some elbow room at the end, and you tack on a new element, you tack on the new element, and then oops, I ran out of memory, and you just compress. You know there's got to be memory left over, and so there's a garbage collection that goes by, and every goes through, and every node is compressed in its adjacency list. And that all happens without malloc or free, because that's too expensive inside a middle of a code. And fortunately, the garbage compaction is very rare. It happens to me at most 1 or 2 times during the whole algorithm. And it's just a sweep over the whole graph. So the time complexity is very fast. Anyway, so it's a very elaborate algorithm. But so take a look at the code if you're interested in the details. What I'd like to do next, though, is look at a different permutation question, which is the permutation to block triangular form. And related to this is this idea of a maximal matching. So it's a very different problem than fill-reducing ordering, but it's related. Okay. When we did the QR factorization, we said, well, let's suppose the matrix is strong Hull. If the matrix is strong Hull, then what that means is you can't permute it into strongly connected components. Okay. So what I'm going to try to, with a zero-free diagonal. So the question is that there sometimes can be the case where you can take a matrix and permute it into block upper triangular form. Block triangular form. Block upper or lower. Where the diagonal has no zeros on it. And if the diagonal is zero-free, I mean, there could be epsilons on the diagonal, but they're all non-zero. If the diagonal is zero-free, and you can then find these are in the adjacency graph of the directed graph. These would be strongly connected components. Each of these then cannot further be decomposed into a smaller upper triangular block matrix. Okay. In terms of the graph now, this is a strongly connected component in the sense that in the graph, so you've got a directed graph. A strongly connected component might look like this. There's a strongly connected component of a directed graph has the property that for any pair of nodes, there's a path there and back again. Like the Hobbit, you know. You go from here and there, and you can always get back. This would be one component. So that's one of those. But once you leave the strongly connected component, okay, if you leave, for example, let's see, to follow the Hobbit analogy, once you leave the uttermost west, right, you enter Middle Earth, okay, you can never go back, let's say. But once you're inside the second strongly connected component, you can go between any node and any node. But you can never go back again. So there's edges here, potentially. Of course, there could be no edges here, but whatever, there may be edges here. They don't have to be, but there can be no edges going back. There has to be a permutation of the strongly connected components so that you can lay them out left to right. So here's a component, here's a component, here's a component, and here's such that all the edges between the components go from left to right. There's no cycles. So if you take the graph and collapse every strongly connected component, and a strongly connected component is maximal in size. It's only a component if you cannot make it any bigger and still keep it to be strongly connected. So it's a subgraph that is as big as possible and yet still have the property that between every pair of nodes in that subgraph, there's an edge there and back again. So that's a strongly connected component. And if you've taken, I guess data structures or the algorithms course, graduate, you've seen this stuff before. So in that case, there's nothing new. But if you haven't seen that, there is something new here. And then so that's the definition of a strongly connected component. It's a subgraph that's as big as you can make it. It's maximal in size, but such that there's a node, there's a path there and back again. These components are always disjoint. They can't overlap. You can't have this, right? Because if there's a node that these two components share, well then they're not as big as they could be. Because these strongly connected component is only called that if it's maximal in size. You cannot make it any bigger. So if there is a path here and back again, and a path here and back again, there's a path here and there back again. So the whole thing would be a strongly connected component. So strongly connected components are disjoint from each other, and together they make up the whole graph. So the collection. So what they do is it breaks your graph into a collection of these disjoint components, subgraphs. Every node is inside one of these components. Then imagine you take these strongly connected components and collapse them into a single node, like this. Okay, so you collapse them into a single node. Now the claim is you've got a new graph and there can be no cycles. The claim is then in the new graph, this component graph, there's no cycles. It's an acyclic graph. It's an acyclic graph because if there was a cycle, this is a component, that's a component, and that's a component. Okay, so this is like a little island of nodes. Okay, and the claim is there can be no cycle among your islands, your connected components. Because if there were, even if it's not the same node here, it could be different nodes. If there were a cycle, well, there's a path from here and there back again, because that's a component. And likewise here and likewise there. That means, and for any node here, in fact, there's a path here to any other node in the component there and back again. So what that means is you can go anywhere from this island to this island, anywhere onto that island, and to here, anywhere on this island, and back to here to anywhere on this island. That means within all three components, there's a path between every pair of nodes in all three. But wait, then I lied. Because I just said the strongly connected components were as big as they could be and yet still be strongly connected. But now I find that, if I have a cycle between these, I could have said, well, hey, the whole thing is one strongly connected component. So there can be no cycles between strongly connected components. So if I take the graph, find the maximal size, the strongly connected components of maximal size, and then I take all those subgraphs and collapse them into single nodes, then the resulting graph is acyclic. It cannot have any cycles. Well, such a graph has an ordering. If I do a topological ordering of this graph, all the edges will go from left to right, and I'll find that I have an upper or lower, as you wish, triangular matrix. So that's the block triangular form. It's just the adjacency matrix of a graph that breaks into more than one strongly connected components. Okay. So that's the idea of strongly connected components. So what's so special about the diagonal? What's so special about the diagonal? Well, it turns out there's several things that are special about it. But the main thing is that consider the case, say for this matrix. It's got zeros on the diagonal. Now if I were to draw the graph of this, it would look like that. And who cares? It doesn't have any self-edges, but that's irrelevant. I can still go there and back again. It's one component. A single component. However, if I swap these rows around, I get this matrix. This is a matrix with a zero-free diagonal. Once I do this, I now have two strongly connected components. In fact, I could have changed this matrix. I could have put a 1 here like this, and I have the same thing, except now I have an edge between them. Okay? So here, so I've got a self-edge, but who cares? I can still get from here to here. It doesn't matter. The self-edge doesn't matter in terms of the connectivity. And so it turns out then, if you want to find these strongly connected components, then these strongly connected components will be, if you have zeros on your diagonal, they could be bigger than they would otherwise be if you did have a zero-free diagonal. But if you do have a zero free diagonal, then these components become unique. Now the ordering might not be unique. You might be able to, suppose this was, let me put some values here. Suppose it was this. You could also do this. You could order it that way. Okay, so you still have two strongly connected components with no edges between them. The order in which you place them might not be unique. Over here, for instance, in this component graph, these two components here could be placed in any order. I could place them this way or reverse them, and I would still have all the edges going from left to right, so that I would still have, say, an upper triangular matrix here. So I could swap some of these around. I could put this one down here and this one up there, and it would still have an upper triangular matrix because this is all 0. So I could swap these two, and I would still have this structure. So in that sense, it's not unique, but it's unique in the sense that all the nodes here would tag along. They would just move in the order, and the sizes of all the components would still be the same. So the moment you have a zero free diagonal, the property is that then the strongly connected component graph is broken into as many components as is possible, and the result is unique. So that's useful. That's very useful. And furthermore, in terms of the numerical accuracy of the algorithm, well, we're not doing any numerics, but what if? So here's the idea. Here's how we can exploit this. So let's look at, say, now we have an unsymmetric matrix, of course. So we're looking at LU factorization, or QR. What if I have a matrix that looks like this, where these are blocks? Okay, suppose that my matrix decomposes into 3 strongly connected components. And it could be 3, it could be 300, it doesn't matter. But of course, then if it was 300, I couldn't draw it. Well, my system breaks into 3 linear systems, not completely independent. Okay, but look at this last equation. This says that A33 x3 equals B3. I can solve this for x3 independently. So I can do an LU factorization of just this matrix. Then this equation says, the next equation up says that A22 x2 plus A23 x3 equals B2. Well, but I already know x3, and so I can write this as follows. A22 x2 equals B2 minus A23 x3, which is, I'll call B2 prime. So the moment I have x3, I now have a new linear system to solve. A22 x2 equals B2 prime. So to solve this linear system, all I need is an LU factorization of this block. And the same thing goes for the last one. So the only blocks, the only part of the matrix you have to factorize are the diagonal blocks. And you don't have to include A12, A13, A23. These off-diagonal blocks do not appear in the factorization. That's powerful. That is really important. Let me give you an example for why that is. Suppose I can break my matrix up this way. And 1 means just non-zero. I just didn't put x's. Suppose that my partial pivoting rule says that, okay, this is the bigger element right here. And I've got to pick that as my pivot. So I have to use this to annihilate this one. Well, look what that would do. That would introduce non-zero values in this upper triangular part if I did this. And that can be very expensive to do. But if instead all I have to do is factor this part, this stays alone. I have no fill. No fill-in over here at all. They just remain. They only have to be, to represent the system and its solution, all I need is the factorization of the diagonal blocks, and I just need to be able to do a matrix vector multiply here with A23 and A13 and A12. That's it. So it's as far as the work goes for all the symbolic analysis and all the LU factorization, you just ignore all that. It's just a matrix vector multiply, which is really quick and easy, and it causes no fill-in. So you've got all the heavy-duty lifting, all the work is done inside the strongly connected components, and there's very little work to do for the edges that connect them at all. And furthermore, if this matrix happens to be psychologically triangular, remember that one project you had where you were given a matrix that's a permutation of a triangular matrix. Well, guess what? If you permute that to find a zero-free diagonal, and then find the strongly connected components, you'll find right away, oh, that's upper triangular. And if you want to give this a try, take a look in the C-sparse CSDM SPI of a matrix, say A. Okay? And don't try it on A, try it on L, and do the following. Try this. LU bracket bracket equals LU of A. Take a sparse matrix, do its LU factorization, but don't ask back for the permutation. What that means is that L is psychologically triangular or morally triangular, whatever. And then pass it into DM SPI. What DM SPI will do, it'll find this permutation and plot it on your screen. It'll create a figure that looks like this. And guess what? It'll be upper triangular. It won't be lower triangular. It'll be upper triangular. Because the lower triangular is just, if you take a lower triangular matrix and apply a symmetric permutation to it, such that you reverse all the rows and reverse all the columns, you get an upper triangular matrix. It doesn't transpose it, it sort of swaps it around. I think, yeah, you have to do both. But it'll show you that. So this is where we're going, and I've got 3 minutes left, so I'll have to give you the details next class. So the idea is the first step in this process is to find a row permutation to make the matrix have a zero-free diagonal. I'm going to model that as a bipartite graph problem, and it's a maximum. I use the word maximal too easily. It's a maximum matching problem of a bipartite graph. I'll show you how that's done. Once that's found, the next step is much simpler. Finding the strongly connected component is done with two depth first searches, one in one direction, and then you transpose the matrix and do it in the other. So that's a problem that comes up in the algorithms course, grad algorithms course. I have 2 minutes. Let me show you really quickly, and I'll at least get it started, explaining what this is in terms of the figure, at least. So the idea is we start off with nothing matched at all. And we're going to go one column at a time and make our match bigger. So we go to a column K that's not matched. And here's the column that's not matched. The very first thing we want to do is when we look at the column, and if it's the very first column, it's very easy. I'm trying to find a row permutation. So I'll look at column 1, and there's a 0 here. Okay. Oh, look. There you are. Just pick it and put it on the diagonal. Just find any non-zero. And if there is none, well, then, of course, there's no permutation to make it the diagonal zero free, is there? This is called a cheat match. And in a cheat match, in the bipartite graph, that would look like this. You look at your neighbor here, there's the columns and here's your rows. So it's a bipartite graph in which you've got all the rows here and all the columns here. And you start off with nothing being matched. So you're going to go through the columns one at a time, where at any given step, these columns are matched, and the next one, the kth one that you're matching, is not matched. So at the moment, nothing's matched. So I look at this, and I'll say, then I look at my neighbors. And now some of these will be matched and some won't. But for the very first one, nothing will be matched. So I'll match this one. So now row 5 is matched. It's married. Right? Column 1 has married row 5, if you will. So they're paired up. And as the algorithm progresses, row 5 may get matched by different columns. So think of it as a dance, probably at a party would be better rather than marriage, right? Because that's supposed to be permanent. It's not permanent. It's going to change, possibly. It may have to be that row 5 has to go to a different column. But if that happens, we find another partner to dance with column 1. And the dance, the matching happens here. So there's the pair up between column 1 and row 5. That's one entry on the diagonal. The goal then is to find a pairing of every row with every column. Once you do that, you've got a zero-free diagonal. The tricky part comes when, what if there's no cheap match? If there's no cheap match, all your neighbors are matched. All your neighbor rows are matched. So the idea is we search through the graph. We go to all my neighbors. From there we go to its match. From there we look at all of our neighbors. From there we go, and then finally we'll find a row that's unmatched. And if this happens, if we can find this, this is called an alternating augmenting path, then we switch the matching. Rather than having those 3 matched with these 3, we switch the match so that those are matched with each other. And now instead of 3 being matched, all 4 are matched. And I'll go into the more detail of that. And this is the matrix view, the same thing. Frankly, the graph view is much simpler to look at than the matrix view. But I'll give the details of this next class. And we'll have to go through that pretty quickly because that's the last class. We'll look at that, and then we'll look at nested dissection ordering algorithm as well in 7.6 very briefly. So those are the main ordering methods: minimum degree, this block triangular form idea, and then the nested dissection idea, the main ordering, and they're all heuristics. This thing is not a heuristic, but it's not reducing fill either. It's just sort of giving a global ordering that will hopefully break the problem into smaller problems. Okay, so I'll see you Wednesday. Thank you.